Okay, let's solve this graphing question. We have a car that starts at the negative 20 meter position with a velocity of negative 9 meters per second. The car starts changing its velocity at a time t equals 0 seconds at a rate of 3 meters per second every second. So that's our acceleration. This happens for 8 seconds. We have to draw the corresponding position, velocity, and acceleration graphs and answer questions 2 and 3. So let's start by creating a table to make graphing a bit easier. So I already have this overlay created that we can just fill in. The easiest thing that's going to be the easiest thing to fill in here is going to be the acceleration, because it's constant throughout the problem. So I can just start filling in here positive 3, take this all the way down. So the acceleration column and the acceleration graph will be the easiest thing to complete for this question. So we'll have a horizontal line on our graph. Next, we're going to move on to velocity. We have the initial velocity at 0 seconds, which is negative 9 meters per second. I'm going to put that here. Now we can do an equation and solve for the final velocity at each moment in time, where Vf is equal to Vi plus 18. But it's easy enough, because the acceleration is constant, to just add the acceleration value to the velocity. So in 1 second, the velocity will change by positive 3. So it'll go from negative 9 to negative 6. And from negative 6 to negative 3. Add 3 again, I get 0. We keep just doing that down the line. So the velocity graph will also be pretty straightforward to draw, because it will be a straight line. Okay, so positive 12 and positive 15. The next part is going to be the position, and this is going to be the trickiest part to answer. So let's see how this works. The initial velocity, the initial position is given to us as negative 20, so I'm going to put that here. Now, how far does the car travel in the first second? To determine that, we can use the equation d equals vit plus 1/2 at squared. But we can also just use the average velocity times time equation. During the first second, I can find the average velocity, multiply by time, and get a displacement. That displacement would be added onto the initial position, and we would get our final position at 1 second. So let's do that right now. I'm going to remove the question, because we have all the information we need here. And I've already set up our graph here for us to use later. Okay, so I'm going to write here the equation for the displacement. Use a different color. Displacement will be equal to average velocity times time. This will be from 0 to 1 second. This will then become displacement is equal to the average velocity from 0 to 1 second will be negative 9 meters per second plus negative 6 meters per second. That's this velocity and this velocity. This is our initial, this is our final, because this is our initial time and this is our final time. And then we divide this by 2. So this will give us our average velocity. And then we multiply by the time interval. The time from 0 to 1 second is 1 second. And so our displacement from 0 to 1 second will be negative 9 plus negative 6 is going to be negative 15 divided by 2 will be negative 7.5. I can also show that to you on the calculator. Negative 9 and negative 6. Let's move this calculator over. Negative 9 plus negative 6 is negative 15 divided by 2, negative 7.5. That's our average velocity. Multiply that by 1 second, and we get negative 7.5 for a displacement. So negative 7.5 meters. But this is our displacement. This is not the number that will go in the column here in the table. We need to remember that this is really a delta x, and the equation for delta x is final position minus initial position. So to find final position, I do some algebra here, because we can show the algebra. We can add initial position to both sides. Yeah, so it's going to be this plus this. These cancel out. And we got our new equation. The final position is equal to the initial position plus the displacement, which means our final position, this is at 1 second, our final position will be equal to, well, our initial position is negative 20 meters. Add the displacement, which we just found out is this, negative 7.5. And we will get negative 27.5 meters is our next data point that goes in here. Negative 27.5. So we have to do this for every 1 second time interval if we use this equation. Another method would be to use the equation d equals vit plus 1/2 at squared. So over, yeah, let's show that for 2 seconds. Or you know what, let's do this same procedure for 2 seconds, and we'll use a different procedure for the next time interval. So I'm just going to erase some values here, because I'm going to reuse this work. I'll change the time. It'll be a different initial position, a different displacement, and we'll get a different answer here. So yeah, I'll use a different color to show what we're reusing. Okay, so let's now do this from 1 to 2 seconds. From 1 to 2 seconds, the average velocity will be, this will be the initial, this will be the final. So it's going to be negative 6 meters per second plus negative 3 meters per second. The average velocity there will be negative 4.5 times 1 second. So our displacement is negative 4.5 meters. Yeah. So now we take this number, that's our displacement, so it goes in here, negative 4.5. And our initial position is now, because we're going from 1 to 2 seconds, the initial position that goes in here is the position at 1 second, which is negative 27.5. Negative 27.5 meters plus negative 4.5 meters. Let's use our calculator. Negative 27.5 plus negative 4.5 gives us a displacement of a final position of negative 32 meters. So this number goes in here. And so you can keep doing that throughout this entire column. So most of the work required for this question is going to be in the position column. The acceleration and velocity columns are going to be very easy. All right, let's try now a different approach to this question. I'm going to erase all this and use the third equation to solve for the displacement. So that will look like this. What is the displacement from, I want to find out the final position at 3 seconds. So I can do, what is the displacement from 0 to 3 seconds? That will be v initial times time plus 1/2 at squared. So the displacement from 0 to 3 seconds will be equal to, because I'm starting from 0, my initial velocity will be negative 9. And the time interval here from 0 to 3 is 3 seconds plus 1/2. The acceleration is a constant positive 3. And again, our time interval is 3 seconds. This is all squared. Now we have to do some math. Negative 9 times 3 is going to be equal to negative 27 meters. Plus, I can do all this on my calculator. Okay, so it'll be 0.5 times 3 times 3 squared is 13.5 plus negative 27. So this here was 13.5 meters. And so our displacement from 0 to 3 seconds is equal to negative 13.5 meters. Then to get our final position, it's going to be equal to the initial position plus the displacement. Again, we need to remember that this is actually a delta x, our displacement. And our final position will be, initial position at 0 is negative 20 meters, plus our displacement, which is negative 13.5 meters. That's going to give us a final position of negative 20 plus negative 13.5 will be negative 33.5 meters. So I'll put that in here, negative 33.5 meters. Okay, so I'm going to erase just these values and reuse this equation. This time it won't be from 0 to 3. We can do it from 0 to 4. Or we can do it from 3 to 4 seconds. Yeah, let's try that. Let's make this time interval from 3 to 4 seconds. So here we go. The displacement from 3 to 4 seconds. The initial velocity at 3 seconds would be 0. Right? Because at time 3 seconds, the velocity is here, 0 meters per second. So that's why I put that there. The time interval from 3 to 4 is 1 second plus 1/2. The acceleration is still our constant 3 meters per second squared. Our time interval again is 1 second. So I do the math here. 0 times 1, this will be 0 meters, plus 1/2 times 3 is 1.5. 1.5 times 1 squared is just 1.5. So this is going to be plus 1.5 meters. So we have a displacement of 1.5 meters. This is a positive value. So I put that in here. This displacement goes in here, 1.5 meters. The initial position, the initial position at 3 seconds, is negative 33.5. This is a positive, this is a negative. So a negative 33.5 here. Negative 33.5 plus 1.5 gives us negative 32. Negative 32 is the position at 4 seconds. Now, of course, I would recommend only using one method for finding the positions for this position column. I'm just showing you different ways that you can go about doing this. Okay, so we have to now do this 4 more times. I'm going to use the average velocity equation because I think it's the simplest one to use. So here we go. We're going to do the displacement from 4 to 5 seconds. Let's use average velocity times time. The average velocity between 4 and 5 seconds here is positive 4.5 meters per second. Multiplied by 1 second, we get 4.5 meters. So the car must have traveled 4.5 meters in the positive direction during this time interval. So if it starts at negative 32, I can now just do this. Negative 32 plus 4.5 meters. And we are now at negative 27.5. We are now at negative 27.5. I'll do it again now for the displacement from 5 to 6 seconds. Find the average velocity multiplied by time. The average velocity from 5 to 6 seconds is going to be 7.5 times 1 second. So the car travels in the positive direction 7.5 meters. So I'm going to add 7.5 to negative 27.5. So now that I have this as an answer, if you have a graphing calculator, I can just click the plus symbol and it will automatically take that previous answer and I can add to it 7.5. It's a positive displacement and I get negative 20. So I can put negative 20 here. Okay, do the same thing. So you can see towards the end, once you get a hang of this, it can actually be done very quickly. Let's find the displacement from 6 to 7 seconds, which is average velocity times time. The average velocity from 6 to 7 seconds is going to be 10.5 meters per second times 1 second, and you'll see it's 10.5 meters. Again, a positive displacement. Let's do the same thing we did before. We add to negative 20, 10.5 meters. And we get a position of negative 9.5. Last one, the displacement from 7 to 8 seconds is average velocity times time. The average velocity during the last second from 7 to 8 seconds is 13.5 meters per second times 1 second. So we get 13.5 meters. I'm going to add 13.5 to my previous answer. And we got positive 4. So we have a positive position now. Positive 4. Okay, so we don't need this calculator anymore. Okay, so you can see I already have a graph set up that we can use to create the graph, to sketch the graph, but you're going to have to draw these axes when you answer this kind of question. Let me erase all this. So all we have is our table and our graphs. Let's start by, let me actually copy this because I can reuse this for all 3 graphs. I'm going to copy this page and I'm going to paste it twice so I can use it for position, velocity, and acceleration. Let's start with the simplest graph, and that's going to be the acceleration graph. So I'm going to label this as acceleration measured in meters per second squared. I already have time labeled here on the x-axis. Okay, so because our acceleration is constant, this is going to be simple to fix this. This is going to be simple to sketch. You have to scale your axes for each question that you answer. So let's use on my grid here. Let's make 5 boxes equal to 1 meter per second squared. So that would be negative 1. That would be negative 2. 1, 2, 3, 4, 5. And that would be negative 3 meters per second squared. And I can just draw a horizontal line there that goes all the way out to 8 seconds. Right, just to show. Yeah, and this is my acceleration versus time graph. That corresponds to the information here in this column. So we're done with the acceleration graph. Let's move on to the velocity graph. It would be over here. Okay, so now velocity versus time graph. Velocity in meters per second. I already have time here labeled. Okay, so to scale the y-axis properly, I have to look at the range of values that I have. This goes from negative 9 is the lowest value, positive 15 is the highest value. So let's scale this out. Let's see, I guess in threes makes sense. So every 3 boxes, I'll just label it as 3. So 3, 6, 9, 12, 15. Positive 15 is going to be my highest value, and then I have to go down -3, -6, -9, -12, -15. Okay, now I can start plotting my data points. At 0 seconds, the velocity is -9, so that's going to be here. At 1 second, the velocity is -6, that will be here. 2 seconds, it's -3. 3 seconds, it's 0. Yeah, at 3 seconds, the velocity is 0, shown here. At 4 seconds, the velocity is +3, so that would be here. 5 seconds, the velocity is +6. 6 seconds, the velocity is +9. So it will always change by +3 each second. So I can put this here. Now I can draw my best fit line. We know it's going to be linear because I have a constant acceleration. You would do this with a ruler. I don't have that option right now. But this should be a straight line, and the slope of this line is equal to +3 meters per second squared, representing the acceleration. Now, for our last graph, we're going to plot the position versus time. Most of our positions here are negative values, so what I should really do is erase this and place my x-axis somewhere further up here. I'm going to freehand this, but of course you should use a ruler. So let's go ahead and label the times: 1 second, 2, 3, 4, 5, 6, 7, 8. This is going to be a position graph. And my lowest value is going to be -33.5. My most positive value is +4. Let's see, how am I going to scale this? 1, 2, 3, 4. Yeah, I guess I can just do it by one box. So this is going to be my +4 value. 1, 2, 3, 4. This is -4. 1, 2, 3, 4. This is -8. 1, 2, 3, 4. -12. -16. -20. -24. -28. -32. We can stop here at -34. Yeah, because our lowest value is -32 anyway. Alright, so now we just start plotting data points. At 0 seconds, our position is -20 meters. So 0 seconds, -20. Here's my first data point. At 1 second, we're at -27.5. So the car starts going in the negative direction because it has a negative velocity. But very quickly, it'll start then moving in the positive direction. So it goes from -20 to -27.5, which is somewhere over here. And then at 2 seconds, it will be at -32. So I move over 1, 2, 3, 4, and it will be at -32. And then it will be at -33.5. 33.5 will be here. And then back to -32. So 1, 2, 3, 4. Back to -32. And then -27.5, which is here. Then -20 at 6 seconds. Let me just double check that. At 6 seconds, we're at -20. Yeah. So that would be 1, 2, 3, 4. That would be 6 seconds. Yep. 7 seconds at -9.5. -9.5 is going to be somewhere about there. And then finally at 8 seconds, it'll be at +4, which is there. Now, of course, you can see here this parabolic shape. We're going to have to do the best we can to do a good best fit line. So we're going to do something like this. So the car starts going in the negative direction, but it's slowing down. As we can see, the slope is decreasing to 0. So the slope is very negative. It's -9 here. And then the slope becomes 0 at 3 seconds, and then it speeds up in the positive direction. Right, so from after 3 seconds, it has a positive velocity. It speeds up in the positive direction, and it ends up at +4 at 8 seconds. So email me if you have any questions, and I'll probably do another one of these in class.